we continue with the solution to the equation y double prime minus y equals t squared e to the t plus cosine t. Remember that we decided to find particular solutions for this equation where the right hand side is just the t squared e to the t, and for the case where the right hand side is just cosine t. We call those yp1 and yp2, the solutions to the two equations into which we've for the moment split this one equation. We've done this with the expectation that if we then add the two particular solutions, we will get a particular solution to the original equation. And we have good reason to think so, because having found a particular solution to this equation, if we plug it into the equation, this is what we're going to get. If we find a particular solution to this equation and plug it in, we're going to get the cosine of t. So that if we plug the sum of the two particular solutions in, we should get t squared e to the t plus cosine of t by the linearity of the differential operators. Recall that we previously solved the second equation, giving us yp2's 1/2 cosine of t. And now we're trying to solve the second equation, and we've seen that we can't use a solution at squared plus bt plus c e to the t to match up with the t squared e to the t, because c e to the t is a solution of the homogeneous equation. So we've multiplied that solution by t, and now none of the terms of this trial solution, this trial particular solution, are solutions to the homogeneous equation, and we're going to proceed. We've already written down the particular solution is this. We've done the derivative of the particular solution without necessarily going through all the details. And then I wrote down the second derivative. And I wrote that down inadvertently, leaving off the constant terms. So this is a little different than what you saw at the end of the first clip. You can take my word for this derivative, but you shouldn't. You should go ahead and start with yp, do the first derivative, and do the second derivative, and see that they come out the way I say they do. Now, if we plug yp and call it yp1 and yp1 double prime into the original equation, we're going to get yp1 double prime minus yp1, and that should equal t squared e to the t, which is our original equation. I guess this is the original equation here, but I guess we're coming back and calling this for the moment the original equation. Okay, if we do that, taking the expressions for yp double prime and yp, again you can check. The result ends up like this. Okay, I'm not going to read it to you. You can see it. And all we've done here is we've taken yp double prime and subtracted the expression for yp, so that our equation becomes this. Now the coefficient of t squared on the left, that's actually t squared e to the t, becomes the same as the coefficient of t squared e to the t on the right, meaning that 6a is going to have to be 1. And there is no t e to the t or constant times e to the t term on the right hand side. So this expression and this expression both have to be 0. So we write it that way, and we solve these equations simultaneously for a, b, and c. I've written down the solution. It should be trivial to solve these, although of course you have to be careful and check your solutions and so forth. But this solution does seem to check out. So having taken those couple of steps, we conclude that yp1, substituting the values of a, b, and c, and also distributing the multiplication by t through here, gives us the equation you see here. Again, you should verify this for yourself. This will be our particular solution, yp1. And now in the next clip we'll combine these two solutions into a particular solution of this equation, and add that to the characteristic solution of the equation, that is the solution to the homogeneous equation.